podcast is brought to you by LMU Munich.
Tremendous pleasure to be here. I'm speaking about a subject, the very first talk of which was actually given at the Strings 2009 meeting. So this is, in a sense, a update and, in many ways, a closure of a good part of some of the, or a more complete understanding of some of the structures that were presented at Strings 3 years ago. This is work that's largely, I'm going to talk about work that's largely done, a short version of which should appear hopefully in the next number of weeks in collaboration with Freddie, Jake, and Yaroslav, as well as two mathematicians, Sasha Goncharov and Sasha Posnikov. We were put on the right mathematical track through some extensive discussions with Pierre Deline and Bob McPherson at the Institute. There's also a number of other collaborators, and at the very end, if I have time, I will also mention some work in progress with Simone Caron-Huot. So there's a conventional picture of quantum field theory that we all know and love, which, starting at spin 1 and higher, requires us to introduce gauge redundancy to make locality and unitarity manifest. And it's been clear for a long time that doing this, introducing this gauge redundancy, obscures the invariant content of the theory that was seen dramatically first at strong coupling in dualities, gauge-gauge and gauge-gravity dualities. Part of the fun of this subject in the past 5–10 years is that we're also seeing that, that this gauge-redundant description of the physics is obscuring beautiful structures that are there even in the home base of the traditional job of perturbative quantum field theory, which was calculating scattering amplitudes. And here, in the past decade, there's been stunning magic revealed in n equals 4 super Yang-Mills in the planar limit. For example, there's this hidden infinite dimensional symmetry. If we lay all the momenta of the particles down, because they're naturally cyclically ordered, if we lay them down on a 4-dimensional sheet of paper, they close to form a polygon. And for instance, the scattering amplitudes are not only conformally invariant, as they should be, that's an obvious symmetry, but they're also invariant under conformal transformations in this dual space. And the conformal and the dual conformal transformations close into an infinite dimensional symmetry, the Yangian. So this is an infinite dimensional symmetry. Dual superconformal invariants could have been noticed at any point since Yang-Mills theories were written down. Even they're a property of tree amplitudes, but they weren't noticed until people knew where to look for them 5 years ago. So what we're after is a theory then for calculating scattering amplitudes without conventional evolution through space-time. So the scattering amplitudes are a function. I won't introduce these spinor helicity variables here, but they're of the spinor helicity variables lambda and lambda tilde that tell us about the momenta of the external particles. These etas are Grassmann variables that group up all the helicities into one nice supermultiplet. If we're at loop order, we might have some loop momenta. N is a number of particles, and k is an important variable. There's a super amplitude here. It breaks up into different sectors, and there's the sector labeled by k is the one that has amongst its component amplitudes the gluon amplitude, with k gluons having negative helicity. So we're after a theory that computes this object without unitary evolution through space-time. That's Feynman diagrams. We want to do it another way. And we're seeing more and more and more systematically what another way is. The beautiful thing about all this, of course, is that, as I said, alluded to already, all this structure has been sitting under our noses for 60 years and is combining ideas now from string theory, twistor theory, spin chains, and also beautiful new structures in algebraic geometry that, quite coincidentally, have just been started to be explored by the algebraic geometers themselves in the last 5 to 10 years, which seem to be lying at the heart of this new way of thinking about scattering processes. Now, in the talk here 3 years ago, there was a lot of things pulled out of nowhere and objects that we're trying to study and understand, as it always is when you first stumble onto something. But now we really understand the story very systematically and can proceed from the ground up. Okay? So I'm going to do that, but just to give you a flavor of what's coming up, and because a very important role in the story is going to be played by a new way of thinking about permutations, I want to go back and remind you of an old way of thinking about permutations that's very closely connected with scattering. So we're going to talk about drawings of permutations and pictures of scattering. So here's a permutation on 5 labels. So, why would you think about a permutation? Well, scattering amplitudes are pretty complicated functions of external momenta. helicities, and so on. If we strip away all of momenta and helicities, all we're left with is the labels. You think we've thrown the baby out with the bathwater, but all you can do with labels is permute them, so let's see, does anything interesting happen just with permutations? Okay, so there's a permutation. It doesn't look much like physics. We can start making it look like physics by representing that permutation graphically on a piece of paper, just drawing arrows to the destination of each label. And now this looks like a picture of scattering in 1+1 dimensions. We have particles 1, 2, 3, 4, 5 down, and they evolve up in time. They undergo 2 to 2 scattering processes in the middle. And in fact, such a picture represents a particular way of breaking up a permutation into a product of adjacent transpositions. Okay? There's lots of ways of breaking a permutation up into a product of adjacent transpositions. This is one of them. There are others. And if you want to demand that the only thing that actually matters is the permutation and not anything else, then there has to be something very special about this underlying 2 to 2 scattering processes that's encoded in the Yang-Baxter equation. So Yang-Baxter just tells you all that matters is the permutation. Something which I didn't say here, but which is also true in these integrable 1+1 dimensional theories, is that there's all sorts of useless diagrams you could draw. For example, things where you just bounce back and forth like that forever. Okay? That doesn't do anything. That's just useless additional complexity added to the diagram. So there's some sort of reduced pictures that you can have without any useless loops in them. And then even those reduced pictures aren't unique. They can be changed into each other by the Yang-Baxter move. Okay, so this is a very old and very beautiful story that relates permutations to scattering in 1+1 dimensions. And people have often wondered, I certainly wondered, can something like this be true in 3+1 dimensions? And it doesn't seem possible. All the features seem very special to 1+1 dimensions. First of all, crucial in this picture of drawing the arrows is that there's no particle creation or destruction. The 5 particles started in the past and ended up at the future. And going along with that, the fundamental interaction is this 4-point interaction, not the 3-point interaction, which is the familiar one that we have in 3+1 dimensions. In fact, in 3+1 dimensions, so much so do we have particle creation and destruction that the way we think of the S matrix is to imagine all the lines are outgoing. And so instead of, we immediately lose the picture of in to out. It's more like vacuum to end things out. Okay? So the whole setup does not seem to work. Okay, but we can take one piece of inspiration. So now I'm going to start the systematic story after that little vignette. But we can take one inspiration from that picture. If there is anything like that that can be true, the pictures cannot be associated with Feynman diagrams. The Feynman diagrams for those 2-dimensional scatterings are complicated as all the diagrams we would normally draw. What the pictures corresponded to were on-shell processes. They were really physical on-shell processes. All the lines in those pictures were on-shell. So if there's any hope, we should learn to talk about on-shell processes in 3+1 dimensions. And this is where all the fun begins. So all the fun begins with the fact that the most basic on-shell process you can have is the 3-particle amplitude. And we normally don't talk about the 3-particle amplitude, but that's because we prejudice ourselves to thinking about real momenta. If we talk about complex momenta, which I'm going to unapologetically do for the rest of the talk, we can certainly legally talk about it. So here are the spinor helicity variables for 1, 2, and 3, and momentum conservation tells me that the sum of these 3 is equal to 0. The lambdas and lambda tildes are both little 2-dimensional vectors, and it's 2 lines of algebra to verify that if this is true, either the lambdas have to be parallel to each other or the lambda tildes have to be parallel to each other. If the momenta are real, lambda tilde is the complex conjugate of lambda, which is why if lambdas are parallel, the lambda tildes are also parallel, and there's nothing to talk about. But if we allow everything to be complex, then it's actually more generally. Either the lambdas are parallel or the lambda tildes are parallel. That means that the 3-particle interaction comes in 2 varieties. The variety where the kinematics is where the one that lambdas are parallel, and the one where the kinematics are the lambda tildes are parallel. Those 2 kinematics go along with 2 different helicity configurations if I'm talking, let's say, about Yang-Mills theory. Okay? So if this is Yang-Mills theory, then the one where the lambdas are parallel, but the lambda tildes are generic, goes along with helicities plus plus minus and is given by that simple and beautiful expression, completely fixed by Poincare symmetry, only completely fixed by the weights, by what these helicities are, simply because it can't depend on the lambdas. It can only depend on the lambda tildes. And it's the other way around for the other configuration. Okay? In n equals 4 super Yang-Mills, all the helicities are unified in one multiplet. And so this thing is beautifully cyclically invariant if you work in a basis that's labeled by these Grassmann coherent states that collects all the external guys into one object. That's the role of this eta. Okay? So now you see something beautifully cyclically, practically permutation invariant in this form. Okay? So these are the elementary objects. Now, what can we do with these objects? If we want to build more complicated diagrams, nothing is virtual here. Everything is on shell. So we're going to take them and we're going to glue them together. But I stress for the 10th time, these are not virtual particles. When I glue these things together, what do I mean? I mean that I identify the momenta. I say this momentum is equal to that momentum. And I integrate over the on-shell phase space of all the internal particles. Okay? So this is a big collection of objects that we might be interested in. In a moment, we'll see that these are of much more than academic interest. The entire scattering amplitude to all loop orders is given in terms of these on-shell diagrams. Okay? So, but anyway, let's just stare at these things for a second. And I want to stress this has nothing to do with n equals 4. You can do this in any theory where the basic vertex is a cubic one. So here is so the left picture is in Yang-Mills, the right picture is n equals 4, but non-planar and so on. In general, this gives us a differential form as a function of the external data. One famous example of an on-shell diagram corresponds to what's known as the BCFW deformation. If you take any previous on-shell diagram, this one, and you add this little black vertex there and the white vertex there is some on-shell momentum that's flowing through there. So we have some new on-shell momenta there and there. So this picture corresponds to deforming the internal guys. And when you work it out, you've actually added one extra variable to what you had before. So if this was whatever form you had before, you have this one extra variable tau, and the new form is shifted. 1 and 2 are shifted according to the BCFW deformation. So this little hat, this little bridge is going to play a very important role in many of the things I'm going to say later. Okay, now why are these things of more than academic interest? Well, the sort of slogan for the on-shell progress in this business in the past number of years is really that the amplitude is completely determined by knowing its singularities. And we know all of its singularities. All of its singularities are given in terms of on-shell diagrams. So this D here, this is a suggestive D. It can mean boundary, it can mean derivative, it can mean singularities of. I'm leaving it suggestive for the moment. But this is really saying that the singularities of the amplitude has two pieces. A piece that looks like an intermediate particle going on shell, standard factorization, and another piece that looks like a loop, where two adjacent particles are merged together. Okay? These are the singularities of the amplitude. This is a very famous looking equation. It comes up in tons of contexts, and it's the central fact about the amplitudes that allows us to determine them. So you can think of that as a differential equation, and we can integrate that differential equation in many ways to come up with objects which satisfy this property. BCFW recursion is one way of doing that. First at tree level and then extended to loop level a couple of years ago. This is what it looks like. So now it's for the whole amplitude, and I'm integrating, so I'm adding one variable. And so here, instead of D here, it's the whole amplitude, and I've added this little bridge, okay, on top of the previous picture. So I've added one extra variable here, and this gives all the tree amplitudes. This gives the corrections that give us all the loops. Now, I don't have time to go through this in detail, but I want to stress something. Every single thing here is on shell. Now, you can say, how can I possibly get something that's a virtual one-loop correction? Aren't the loop momenta off-shell? Where's all the usual off-shell stuff going? Well, it's here. It is all here. What we normally call a D4L at one loop, let's say, is represented here as an on-shell integral over this intermediate line and over the shift, the BCFW shift of the adjacent guys. Okay? So L is lambda lambda tilde plus tau lambda 1 lambda 2 tilde, but it's purely given in terms of on-shell data. Everything is given in terms of on-shell data. So that's why there are more than academic interest. Okay, now, let's now come back. In the previous, now we know the suite of objects that something nice might happen with, analogous to the Yang-Baxter story. So let's go back and ask, now that these are our on-shell processes, is there a way of associating a permutation with them? Again, we don't have a picture where some things go from the past and evolve to the future. Everything's out on the boundary. So how can we possibly associate a permutation with it? Well, it turns out there is a beautiful way of associating a permutation with it that the mathematicians have been discussing since around 2004 or 2005, which is the following. So I'll tell you the rule for how to read off a permutation from one of these pictures. Start, if you want to know where does 1 go, so here I've done an example just for the 3-particle amplitude, where does 1 go? Walk into the graph, and if you hit a black vertex, turn right. If you hit a white vertex, turn left. Okay? That gives you a rule, 2 minutes, 20 seconds thought convinces you that that actually gives you a permutation no matter what the graph is. And so that's a way of associating with one of these on-shell graphs a permutation, this left-right path. Okay, so these are the simplest ones, but you can glue them together to get more complicated ones, as in this example. Now, in fact, it's a slightly extended notion of a permutation. A permutation only depends on n, but actually this notion of a permutation naturally comes equipped with a k as well. The reason is that we have a natural ordering for the particles on the boundary, so it makes sense to always have the permutation move to the right. And so if we just declare arbitrarily that 1 is the start, so you see 1 goes to 3, 2 goes to 4, but 3 goes to 1 is jumping backwards. 4 goes to 2 is jumping backwards. We can always declare that everything is moving forwards just by adding n instead. So we say 3 goes to 5, 4 goes to 6. And k, the notion of k, is the number that jump backwards. So the permutations, they're called affine or decorated permutations, are associated with an n and a k, which is exactly the data, of course, that's associated with the amplitudes. Now, there's clearly an enormous redundancy here. There's a finite number of permutations, but an infinite number of diagrams that I can draw, just as in the Yang-Baxter case. We could tootle around forever doing these useless loops. So here, too, there are a lot of what look like useless loops. There's a notion of a reduced graph, a graph of the smallest number of faces that realizes a given permutation. In a second, we'll see that even those useless loops have a point in life. They are the loop amplitudes. Those where all the information about the loop integrand and the loops are actually hidden, but we'll come back to that in a second. Okay, but even now that we've reduced to the reduced graphs, there's still a redundancy. And the redundancy is given by the following 2 basic moves. You can do any sequence of black vertices together and merge and unmerge them any way you like. That obviously doesn't change the permutation. So you can, in fact, if you like, glue them all together so that there's a super vertex with all black vertices and all white vertices. If you do that, the graph becomes what's known as bipartite, where the only edges connect black to white. And so that's trivial. This is also almost looks trivial, but is actually the whole non-trivial content of this structure is what's known as the square move. So you take this little 4-particle guy, you just flip the colors. The permutation, any permutation is obviously the same. You just go around the square in the other order. Now, it is not obvious, but every permutation can actually be represented by one of these bipartite graphs. So this is a result that was proven by Dylan Thurston back in 2005. Using an interesting construction, and actually thinking about the physics suggests another way of solving this combinatorial problem, much more physical, which I'll tell you about in a second. But anyway, it turns out to be true. So not only are each one of these pictures associated with a permutation, but every permutation, every decorated permutation, every affine permutation can be represented in this way. Okay, a final little bit that I'll tell you before jumping to the physics is that these permutations are in bijection with 2 other natural and beautiful mathematical structures. That this is this whole subject, I should say, has been explored by Goncharov, has been explored specifically for this positive Grassmannian by Postnikov. So, and the physics way of thinking about it also suggests a number of new ways of arriving at some of the results, as well as generalizations and other things. But let me just tell you a little bit of what's known ahead of time. So, the permutations play another role. I'll just have to say this very, very quickly. If you have switch topics, we have a bunch of vectors. We have n vectors in a k-dimensional space, and we might want to stratify this configuration of vectors by finding the sorts of by classifying them according to the sorts of linear relationships that they can have between each other. And it turns out that what allows for a beautiful stratification, which is relevant for us, is classifying linear relationships between chains of consecutive vectors. That's the important word, that it's chains of consecutive vectors. Okay? So here's the configuration of of 6 points in P2. The thing that's special about it is that 1, 2, 3 are on a line. And all the information about what's special about this configuration is actually captured in a permutation, an affine permutation, A to P of A, where A is contained in the span of A plus 1 through P of A. It turns out giving that data completely specifies what the configuration is. And another object is the positive Grassmannian. So again, these things are all in bijection with each other. What I told you before was everything was complex. We're only interested in linear relationships. Now we're dealing with real variables. And the positive Grassmannian is the generalization into the Grassmannian of a notion of a simplex, the inside of a triangle in a projective space, let's say. So if you have a k by n matrix, again, you have kn dimensional vectors. Now we imagine all these variables are real, and you can define what you can call the positive part of the Grassmannian by the requirement that all these minors are positive. All the minors are positive. All these k by k minors of this k by n matrix are positive. Geometrically, that means if you draw these points and you literally draw the line that connects one point to another, to another, to another, that the polygon that's formed by them is convex. So it's a convexity condition. And again, making these configurations more special turns out to, for example, if I look at this and I want to make 6, 1, 3, put them on a line, I can't do it because before I get there, 6, 1, 2 are on a line, and then this thing wouldn't be convex anymore. So the boundaries of this space are actually in one-to-one correspondence with consecutive linear dependence between consecutive vectors. All right. So why do any of the? So I told you how to associate a permutation with these on-shell pictures, and I jumped to the end to tell you that also configurations of vectors and cells of the positive Grassmannian are labeled by this permutation. So now let's see how the map goes explicitly. And as I said, it's the physics that tells us exactly how to do it. So let's go back to this picture. You would think there's no nicer way of representing the 3-particle amplitude than that, but it still leaves something to be desired, because this form doesn't make it clear that all the lambdas are parallel, or all the lambda tildes are parallel. So you might be motivated to find a form that makes that obvious, and there is a form that makes that obvious. Quite beautifully, you can write it like this, that makes it totally manifest that the lambdas are parallel to each other, and the remaining delta function gives you momentum conservation. Now, this also looks nicer in twistor space. Anyway, this is the beginning of seeing the Grassmannian. So already for the 3-particle amplitudes, you see that the nicest way of representing the 3-particle amplitudes that makes the geometry obvious represents them as an integral over G13 and G2, 3. So just staring at the 3-particle amplitude tells you to think in terms of the Grassmannian, but also it makes it trivial to glue everything together. The hard part of gluing things together when everything is functions of lambdas and lambda tildes is that momentum conservation is the quadratic constraint. But this representation of the 3-particle amplitude linearizes that and allows you to trivially integrate over the internal variables. What you're left with is, so having written these things down, you just have a linear equation for the black vertices, 2 linear equations for the white vertices. You eliminate the internal guys, and what you're left with is a sequence, k equations, k linear equations that relate to the external data. So if you have n points, doing this, merging together all of these objects, something which in the math literature is known as amalgamation. Amalgamation of these black and white vertices builds from all these little G13s and G23s a point in the big Grassmannian GKN. And when you study in more detail, even though the way I presented it makes it seem that the variables are associated with the vertices of this graph, in actuality, the invariant data is associated with the faces of these graphs. Slightly more redundantly in terms of edges with GL1 redundancies on all the sites, so a flat connection on the graph. Okay? And in fact, there's a perfectly explicit way of writing down the final result that you get with a nice gauge fixing that gives a so-called perfect orientation to this graph. The variables associated with the edges now of this picture, the orientation means that there's 1 arrow in, 2 arrows out for white, and the other way around for black. And you get a concrete k by n matrix with a k by k identity block, and the non-trivial pieces have to do, there's some sources and sinks, and the non-trivial pieces are just the sum over all the paths that you can take from I to j, multiplying by the edge variables along each path. Okay, so that's a completely concrete map from one of these on-shell diagrams into the Grassmannian. Now, the measure, turns out, as I've shown you, it's just obviously just d edge over edge or d face over face. This is something especially beautiful about n equals 4 super Yang mills. The measure is trivial. It's just d log, d log, d log, d log, d log of all of the edge or the face variables. In fact, this map from on-shell diagrams to the Grassmannian is universal. It's true for any theory with cubic interactions, phi cube theory, anything. But it's the measure which depends on the theory. And it's the measure, which is a bunch of d logs, which is particularly simple and beautiful for n equals 4 super Yang mills. Now we can go back to the equivalences that we saw before, just at the level of permutations, and we see that they're reflecting precisely changes of variable that you can make that leave the point in the Grassmannian fixed. So these are the non-trivial things. The move, which is just trivial as I advertised, but this flipping black to white, which physically is nothing other than the fact that the 4-particle tree amplitude is parity invariant, something as trivial as that. Maps, however, that tells you that if you have these face variables here, they have to change to these other face variables on this side. People who know about cluster varieties, of which the positive Grassmannian is an example, will recognize this as a cluster transformation. And its origin is completely transparent here. There's one other thing which is very important, which is also obvious in this language, which is that if you have a big complicated graph, if you do these various moves and so on, you might find a situation you make a little bubble, and you can get rid of the bubble. Okay, so this is what allows the infinite number of graphs to actually be reduced to a finite number of things. All right, so I'm out of time, but let me just say quickly that so we have this whole suite of graphs that are related by these moves, and the invariant content is given by this permutation, okay? by following this left-right path. Everything you might want to know about it. Is the graph reduced or not? Anyway, almost all the non-trivial content has to do with studying this permutation. What's special about the point in the Grassmannian that you end up with is that you have a particular linear dependence between these vectors, which is exactly the one that's associated with that permutation. And if the variables are real, the part of the Grassmannian that's being painted by these on-shell diagrams is inside the positive part of the Grassmannian. BCFW, which is such an important thing physically, is also very important as far as the permutation is concerned. It's an adjacent transposition. And we know that we can actually build all permutations up from adjacent transpositions. If we generalize that notion slightly for these affine permutations, we find a new way of building a picture associated with every permutation that really corresponds to a picture of starting from the vacuum and gradually adding complexity until you get to the final result. Okay, so I won't go through all of this. Just one thing is that this is the form that we started exploring 3 years ago that I talked about at Strings 2009. So far, I haven't mentioned it at all, but we now understand its purpose in life. So there's this measure on the Grassmannian that's just d log, d log, d log, d log. That's a very beautiful measure, but it's given in particular coordinates. You can ask, is there some invariant way of writing this measure? And the answer is yes. That's the invariant way of writing, the form that we'd written down 3 years ago. Very amusingly, because it's not normally the way the interactions between physicists and mathematicians work, this was a situation where it took us a month and a half of talking to Goncharov before we realized that we were talking about the same form. That's the reason, because the mathematicians were using particular coordinates and the physicists had written down the invariant form. But that's what it is. But it does more than do something pretty. This form makes dual conformal invariance completely obvious. I don't have time to review the argument. This is already something we noticed 2.5 years ago. But the purpose in life in this form is that it makes dual conformal invariance totally obvious. If you want to go from a space to the dual space, the on-shell diagrams don't stay the same, but the action on them is most simply represented on the permutation. You just drop the permutation by 2. And also, this infinite dimensional Yangian symmetry is a completely obvious symmetry in this setup. Okay? If you have a measure which is a bunch of d logs, it obviously has an enormous symmetry, namely rescale any variable by any function of the other variables. And geometrically, those are positive diffeomorphisms. Those are diffeomorphisms that leave the positive part fixed. The Yangian, the non-trivial part of the Yangian is just that. It's just diffeomorphisms that keep the positive part fixed. So I won't describe that in detail. Okay, so finally, let me say that we already had 2 years ago this all-loop recursion formula that allowed us to, to explicitly write down what the integrands are that you have to integrate in order to get the amplitude. So there's no thought or work or experimentation or ansatz. You just press return and you get the answer. Okay? It's a completely explicit formula. And that allowed us to write down these very, very compact expressions. That single term summed over these various indices for the 2-loop MHV amplitude, 2-loop NMHV, 3-loop MHV. These things all fit on the line. But the new thing that now we understand the positive Grassmannian is that we understand that those integrands are presented naturally in a new way that we did not anticipate, which is not just thought of as some functions of momenta, but represented as d log, d log, d log, d log, d log. Okay? So I won't go through that. That's something that's even something there that's for a very familiar one-loop integral, one-loop form, this thing that we've seen all the time, turns out to be 4d logs. To see it as 4d logs, you have to recognize not just the importance of the 4 external points there, but the fact that given 4 points in space-time, there are 2 complex points that are null separated from them. And once you know about those points, then there's this beautiful d log representation of it. But now, it's not special. There is an engine. So there's all the one-loop MHV amplitudes in d log form. Here's a local form for all the 2-loop MHV amplitudes. So it's remarkable. There's a change of variables that turns loop integrands into d log, d log, d log. And this fact is not at all obvious from any space-time perspective, but is handed us on a platter in this Grassmannian picture. And I think, and I'll end with this, I think that this is important because it suggests a new way of actually doing the loop integrals. Now, why does doing the loop integrals matter? Not because we care so much to get complicated functions of the external data, but because it's doing the loop integrals that's actually going to make contact with any putative worldsheet description. Any string description of these questions clearly does not have the space-time loop momenta running around. It has a totally different structure controlling it. So we have to get rid of all this redundant stuff sitting there in space-time loop integrals. And the fact that they're presented in the form that looks like a bunch of d logs, which naively makes you think they would integrate to 0, actually suggests a new space-time picture for how to do the integrals. So since I have 0 time, I will not tell you how that works, but I'll tell you that to expect a paper on this with Simon Caron-Huot in the next month or so. But there's a new space, so all the usual approaches doing loop integrals, going back to Feynman and Mellin space and all this stuff, do the integrals in an auxiliary space. We are doing the integrals in space-time. And we can do them in space-time because of the existence of these d-log forms. For example, integrals for 4 external particles localized to a 2-sphere in space-time. 2-dimensional integral, where that 2-sphere is the one that the 4 points sit on. All right. I don't have time to explain to you how Yang-Baxter and ABJM are special cases of the story that I told you about. So let me just end. So I think we are seeing quite concretely some very primitive ideas that seem to underlie at least one way of thinking about scattering amplitudes. And part of the motivating thought for this entire story was that locality and unitarity are not supposed to be the stars of the show, and they're not the stars of the show. There's a lot of other places where this structure shows up. You'll hear at least one more talk in this conference where these black-white graphs, these moves, these permutations are going to show up in totally different contexts. Maybe it's accidental, maybe it's deep, but every context in which they have shown up, and this whole story of cluster varieties, every context that it shows up is somehow related to the 2-0 theory. So it's natural to ask whether we can see this structure also in 6 dimensions. And I finally want to say that I think the very big frontier, next frontier in this general subject is to try to see whether we can find a dual formulation, since this is a string theory conference, I thought I'd end with this, of string scattering amplitudes, not just gauge theory scattering amplitudes. String theory's attitude towards gauge redundancy is the more the better. So given that there is some way of talking about gauge scattering amplitudes, which is removing as much of the gauge redundancy as possible, perhaps there's some way of doing that for string theory as well. We'll hear a talk about string amplitudes after the break, and we'll hear a talk from Freddie afterwards about some amazing recent progress he and his collaborators have made on gravity amplitudes. Gravity is part of string theory, so hopefully that augurs something wonderful for a possible dual description for perturbative string amplitudes. Thank you.
Thank you, Nima. Before taking 2 or 3 questions, I would like to make an announcement. So just after the discussion session now, please walk out this door and then pass by all the coffee. Don't drink any coffee. Go out the building to this beautiful fountain, because then we all assemble and take the conference photo. And once this is successfully taken, with sufficiently many smiles, we can all go back and have coffee. So now ask for questions.
Yeah, so I had somewhat of a question, somewhat of an idea. So maybe if I know that you do everything in momentum space, and then you put in the position space the final result. But if you were to put intermediate steps in the position space, so you have a complex momentum. So if you put complex momentum into position space, you will get real exponent.
You asked me this question on Friday, and I'll give you the same answer I gave you on Friday, which is that we imagine everything for complex momenta, but if you want to compute some amplitude at the LHC, you convolute with real wave packets with real momenta, and that's it.
So if you understand how to do a loop calculation, not integrating over the momentum, but
right,
using some type of understanding coming from your graphs, and trying to make contact with some worldsheet theory. I had 2 questions about that. Do you, A, expect it to have any constriction on the size of the gauge group? And secondly, is it a construction at this point that's valid mainly for large N?
Well, so far, well, except for the some number of slides I skipped in the middle that told you the beginning, that was about the beginning of the story going beyond the planar limit. Everything I actually talked about was planar, first of all. But just to say a little bit more about what the fantasy is that there's clearly some nice structure that controls these integrands, and they're being spat out in unfamiliar forms with d log, d log, d log, d log. Now, I've thought for a long time, for 8 months, I've been obsessed for all this time with trying to actually use that to do the integrals. Again, not because I care about the answer, but because the d log, d log, d log is making it look like almost all the information is redundant, and it's going to localize to something. Okay, so these seeming big 4-dimensional integrals are going to localize to lower dimensional integrals. They had better localize, because we know that we only get dilogarithms that 1 loop, for example, and that looks like a 2-dimensional integral, not a big 4-dimensional integral. Okay, so there's lots of technical obstructions and things that we had to get over, but it's starting to work. So it's working in the sense that you don't do the integral in an auxiliary space. You don't introduce Feynman parameters. You don't go to Mellin space. You take this d-log form that you're handed, and you see that the integrals are almost total derivatives, but they don't localize all the way to nothing. They localize to lower dimensional surfaces that live in the space-time. Now, the hope is that not that we'll eventually do all these integrals. I didn't show it, but even as you might have a hope for calculating or classifying or characterizing all the polylogarithms that might emerge. But we get way beyond polylogarithms already at 2 loops. There's elliptic integrals at 2 loops. There's a K3 surface at 3 loops. There's much more complicated things than polylogs. So I suspect there's not going to be some analytic understanding for actually literally calculating these things. That should not be the goal. The goal should be to find what the theory is on these lower dimensional surfaces that's producing directly these integrands. And since we're now starting to be able to build an engine for going from loop integrands to these lower dimensional integrands, the hope is that that's going to help make contact with the worldsheet description. I don't know what the purpose in life of these lower dimensional constrained integrals would be otherwise. So if there's any justice in the world, hopefully they'll have something to do with the worldsheet description, but maybe they won't. I can certainly say, just to say one more thing, I can certainly say that the usual way of doing things in the auxiliary space, in Feynman parameter space or in Mellin space, at least as far as I can see, and maybe I'm wrong, but as far as I can see, they shed very little light on why the answer has the structure that it has. And also, this new way of doing the loop integrals is completely blind to whether the external data is complex or real, or it's very, very general. Whereas, and going to complex momenta has been important for this story. Whereas all of the usual ways of doing loop integrals collapse immediately when the external momenta are complex. Okay, all of the rules, Feynman parameterization, everything goes out the window when the external momenta are complex. So I take these as some indication that this might end up being a better way of thinking about things, but we'll see how it goes.
Any